NASA went to the dark side of the moon expecting to study hidden terrain, but what it uncovered changed the way scientists look at the moon itself. The farther NASA pushed into that unseen half, the stranger the picture became, and the more it became clear that this was not just the backside of a familiar world. In this video, you are going to see why the far side of the moon became one of NASA's biggest scientific shocks, and how each new discovery made the mystery deeper, not smaller. But before we continue, please subscribe to the channel to give your support. Let's continue. People call it the dark side of the moon, but that is the first thing you need to correct, because it is wrong. NASA did not find a side of the moon that never gets sunlight. The moon is tidally locked to Earth, which only means the same side always faces us. Both sides still get day and night as the moon goes around Earth, so the far side is not permanently dark. And once you clear that up, the real mystery gets stronger, not weaker. If sunlight is not the reason, then why is the far side so different from the side we know? That is where NASA changes the story. Before spacecraft, the far side was basically unknown. People could talk about it, guess about it, make myths about it, but they could not actually study it. Then space missions turned that hidden half from rumour into something measured, mapped and compared. And once NASA got good data, the moon stopped looking simple. So when people ask, what did NASA find on the dark side of the moon? The honest answer is already more interesting than the myth. NASA found that the far side is not just the back of the same moon we know. It is a very different hemisphere, with different terrain, different crust, different volcanic history, and a much rougher record of ancient impacts. The problem is not darkness. The problem is asymmetry. And NASA did not get there with one lucky photo. It built that picture with years of hard data. The Lunar Reconnaissance Orbiter, or LRO, has been operating since 2009, and it became the longest-lived lunar orbiter in history. It worked from a science orbit about 31 miles above the moon, around 50 kilometers. That is close enough to map the surface in detail, close enough to build a modern atlas, instead of just taking dramatic pictures. NASA says LRO helped produce a detailed topographic map covering more than 98% of the moon, and in its primary mission alone, it returned more than 192 terabytes of data. That matters because this is the point where the far side stopped being mystery in the old popular sense and became a real science target. NASA was not just looking at shapes on the surface. It was measuring height, slope, temperature, composition, lighting, and surface texture. It was taking a place people used to talk about, like a legend, and turning it into a data set. So then the next question becomes simple and much more serious. What does that data set actually show? It shows that the far side does not look like the side of the moon we are used to. The near side, the side facing Earth, has those wide dark patches called maria. Those are giant lava plains. Long ago, huge impacts opened massive basins, and molten rock rose up and filled them. That is why the moon from Earth looks marked by dark, smooth regions. The far side is different. It has far fewer maria. It has more highlands, it has more craters. It looks brighter, rougher, older, and less resurfaced. In simple terms, the near side was modified much more by volcanism, while the far side kept a harsher record of the moon's early history. And that difference is not small. It is visible right away, even in basic maps. But NASA's work showed that this is not just a visual contrast. It reflects real differences in the moon's structure and evolution. The far side is not just the near side with a different camera angle. It is a different geologic story. That is why this opening section has to move fast and hit clearly. You are not correcting a minor detail. You are replacing the old mental picture of the moon with a better one. Most people grow up thinking the moon is one familiar object, and that the far side is basically more of the same. NASA showed that this is not true. One hemisphere has broad volcanic plains that dominate how humans picture the moon. The other hemisphere preserves a much more cratered and ancient surface, and the scale makes that even more intense. The moon is about 239,000 miles away from Earth, around 385,000 kilometers. It is one of the most familiar objects in the sky. Humans tracked it for thousands of years. It shaped calendars, navigation, and storytelling, and still half of it stayed out of view for nearly all of human history. People did not see the far side until a Soviet spacecraft flew past it in 1959. That is an important point for pacing, because it shows how recent this really is. For almost all of human history, when people talked about the moon, they were talking about only one half of it. The far side entered science late. And when modern missions finally studied it properly, the result was not a small update. It was a correction big enough to change how we think about the moon as a whole. So the real hook is not that NASA found something spooky. The real hook is that NASA found the moon is not balanced in the way people assumed. The side facing Earth and the side facing away are not twins. They do not preserve the same history. They do not show the same amount of volcanism. They do not have the same surface character. They may not even offer the same scientific value. That is why this first section needs to end on a hard line. NASA did not discover a dark side in the myth sense. NASA discovered that the moon has a radically different far hemisphere, and that changes everything, because now the moon is no longer just familiar, it is uneven. And once you understand that, the next question gets much more important. Because if the far side looks older, rougher, and less flooded by lava, then something deeper must be different too. So what did NASA find under that difference? It found that the far side is built on a thicker shell of rock, and that one fact may explain why the moon split into two very different worlds. NASA found the far side is built on a thicker shell of rock, and that single difference changes the whole moon. Up to this point, you can still tell yourself the far side only looks different on the surface. But this is where that idea breaks down. NASA's data shows the crust is not balanced. On the near side, a representative crustal thickness is about 25 miles, or 40 kilometers. On the far side, it rises to about 37 miles, or 60 kilometers. That is not a tiny variation, and it is not the kind of difference you can ignore. That is a structural difference built into the moon itself. So now the question becomes very direct. Why does that matter so much? Because crust controls what can reach the surface, or what it gets trapped below it. If you want to understand the moon, you have to stop thinking only about what you can see from above, and start thinking about what magma was trying to do from below. Molten rock inside the moon does not rise through empty space. It has to force its way upward through solid crust. And if that crust is thicker by about 20 kilometers, around 12 miles, that changes the whole outcome. That extra thickness is not just more rock. It is more resistance, or more pressure, more distance for magma to cross before it can erupt. So when NASA looked at the far side and saw fewer dark basalt plains, it was not just seeing a visual difference. It was seeing the result of a harder path to the surface. The far side had more rock in the way, and in many places that was enough to stop huge volcanic floods from ever breaking through. That helps explain one of the biggest contrasts on the moon. The near side has those giant maria, the dark plains that define the moon's familiar face. The far side is still dominated by bright cratered highlands. So when you put the crust numbers next to the surface maps, the story starts to lock into place. The near side was easier for magma to break through. The far side was harder to penetrate. Same moon, different barrier. And that is a major upgrade in the story, because now you are not just saying the two sides look different, you are saying they evolved differently because they were built differently. This is the point where an old visual mystery becomes a geophysical one. People noticed long ago that the far side had fewer dark plains. Even before modern missions, that part was obvious once spacecraft finally sent back images. But seeing the difference is one thing, explaining it is another. NASA tied that old visual contrast to crustal thickness, elevation, composition, and gravity. In other words, it stopped being a question about appearance and became a question about planetary structure. That is a much stronger question. Not why is one side prettier or rougher, but why did the moon cool, freeze, and evolve in such an uneven way? Why did one hemisphere get so much more volcanic resurfacing, while the other kept more of its battered ancient face? And once you ask that, the moon gets harder to simplify. Because the near side did not just get lucky once, it seems to have gotten the volcanic jackpot. NASA's broader lunar formation work keeps connecting the near side to more volcanic flooding and to more heat-producing elements. That means the near side was not only easier to break through in structural terms, It may also have had stronger internal conditions helping magma stay mobile for longer. More heat, easier pathways, more foul, more eruption. That combination matters. The far side, by contrast, looks like the place where that process struggled. Not completely dead, not completely inactive, but much more restricted. Magma seems to have had a harder time crossing the crust there, and that left the surface looking older and less flooded. So you should not describe the far side as boring, because that misses the point completely. It is the hemisphere where the moon's interior lost the race to the surface. That line matters, because it gives you a simple way to understand a complicated geologic story. The near side shows where the moon vented heat efficiently. The far side shows where that venting was much more limited. One half released more of its internal energy onto the surface. The other half held more of its old structure. And the result is something much bigger than a map difference. It means the moon is not one clean record. It is two different records sitting on the same body. So ask the next obvious question. If the crust is uneven, what does that do to the moon's history? It changes how you read everything. Craters no longer mean exactly the same thing on both sides. Volcanic plains no longer mean the same thing on both sides. Even surface age has to be read through the filter of crustal structure. A thinner crust gives magma more chances to reach the top and reset the surface. A thicker crust means more of the older impact record stays exposed. That means the near side and far side are not just different landscapes. They are different archives. The near side tells you more about volcanic flooding and thermal release. The far side tells you more about what the moon looked like, where resurfacing largely failed. That is a very important distinction, because it means the far side may preserve a more direct record of early lunar history, while the near side preserves a stronger record of internal activity reaching the surface. This is where the whole moon changes shape in your mind. Before this, people tend to picture a uniform world with cosmetic differences. After this, that picture stops working. You are looking at a body whose two hemispheres preserve different chapters of the same story. One chapter is about eruption, flooding, and change. The other is about resistance, impact survival, and incomplete resurfacing. And that makes the moon much more interesting, because now every major feature becomes part of a larger asymmetry. The Maria are no longer just dark spots. They are evidence that one side was more open to magma. The battered highlands of the far side are no longer just rough terrain. They are evidence that one side stayed more sealed, more ancient, and more exposed to the long record of impacts. That is why this section matters so much. NASA did not just find that the far side has thicker crust. NASA found one of the reasons the moon split into two very different geological worlds. That thicker shell helps explain why the near side became the moon people recognize, while the far side kept a harder, older face. And once you understand that, the next step gets even more intense. Because a thicker crust does not just affect volcanism, it also helps explain why the far side preserved so much damage, and why it became the moon's impact archive. The far side is the moon's impact archive. And the reason is simple. Almost nothing there erased the damage. On Earth, when something hits hard enough to leave a giant crater, time usually starts destroying the evidence right away. Wind wears it down, water cuts through it, tectonic plates shift the crust, mountains rise, oceans cover old terrain, and whole sections of surface get recycled back into the planet. Earth keeps moving, so Earth keeps deleting. The moon is different. It has almost no atmosphere, no liquid water, and no plate tectonics. So when something slammed into the moon billions of years ago, the mark often stayed there. And the far side kept even more of that record. That is the key point in this section. The far side looks packed with craters, but that does not mean it got hit in some completely different way from the near side. It means much less of the evidence got covered up later. The near side had more volcanic resurfacing. Giant basalt floods poured into big basins and smoothed over older scars. The far side had much less of that. So when you look at it, you are seeing a surface that stayed exposed longer and changed less. It is not overcrowded. It is under-erased. That one idea changes how you read the entire far side. Those craters are not just random damage. They are surviving history. And this is where the moon stops being just a moon story. Because when NASA studies the far side, It is also studying a time in solar system history that Earth mostly lost. Early Earth got hammered too. The young inner solar system was violent, big impacts were common, and rocky worlds were taking repeated hits. But Earth does not preserve that era well, because Earth is too active. The crust got recycled, the oldest surfaces got destroyed, and later geology wiped out much of the record. The Moon did not do that. So, the far side matters, because it kept a cleaner archive of the same violent era that also shaped Earth. In very direct language, if you want to understand how bad the early impact environment really was, the Moon can still show you evidence that Earth mostly erased. And the far side may show it best, because less resurfacing means more of the old record stayed readable. That is a serious change in stakes. NASA is not just looking at holes in the ground on another world. It is reading part of the early history of the inner solar system, including the period that helped shape the environment the young Earth had to survive. So then the next question gets sharper. Because if the far side is covered in craters, how do scientists get real information out of that without it just turning into visual clutter? The answer is that crater density is not clutter at all. It is timing information. Every crater tells you that something hit. Every overlapping crater tells you which event came first and which came later. If one rim cuts across another, you know the one doing the cutting is younger. If a basin is buried partly under later impacts, you know the basin is older. If a region is saturated with craters and shows very little resurfacing, you know it has been exposed for an extremely long time. Scientists can read sequence, intensity, and even aspects of the Moon's thermal and structural state from how those impacts were preserved. So the far side is not chaos, it is ordered damage. It is a layered record written in broken rock. That matters because once you stop seeing craters as just scars, you start seeing them as data points. A preserved basin tells you about the energy of the collision that made it. It tells you how the crust responded. It tells you whether the impact melted rock, fractured deep layers, or opened pathways for later volcanic activity. A heavily cratered plain tells you that little came along afterward to reset the surface. A smoother area tells you something did. The surface starts speaking, but only if enough of the old evidence survived. And that is exactly why the far side is so important. It forgot less. There is also a number here that really helps reset your mental picture of the Moon. NASA notes that mare basalts cover about 17% of the lunar surface, and most of that is on the near side. That is a huge point, because the Maria dominate how the Moon looks to us from Earth. Those dark plains are so visible that people naturally think they represent the Moon in general. They do not, they are visually dominant because we face them, but across the whole Moon they are still a minority feature. That means the dark patches most people think of as the normal Moon are not the default Moon at all. The cratered, highland-rich far side is actually closer to the Moon's older baseline state. That is one of the strongest perspective shifts in the whole documentary. The familiar Moon is not the standard version. It is the modified version. The far side, rougher and more battered, is in some ways closer to the deeper original condition of the lunar surface. So when NASA mapped and studied the far side, it was not just finding more damage than expected, it was finding a less edited Moon. And that should hit hard because it means the far side is not valuable in spite of all those craters. It is valuable because of them. Those impacts stayed legible for billions of years. They were not erased by rainfall, rivers, forests, tectonic plates, or large-scale recycling of crust. They remained exposed, layered on top of each other, preserving a timeline of collisions that shaped the Moon and reflect the wider chaos of the early solar system. The far side is what a rocky world looks like when ancient impacts remain readable for an almost impossible amount of time. It is what history looks like when nature does not keep wiping the board clean. Every crater becomes evidence. Every basin becomes a surviving record. Every heavily battered region becomes a page that was never torn out. And once you understand that, the tension goes up again. Because if the far side preserved impacts this well, then the biggest impact feature on the Moon should be one of the most important places in the entire solar system. And it is. Because on the far side, NASA found a basin so large it is not just a crater, it is a planetary scale wound. South Pole Aitken Basin is where the far side stops looking like a rough surface and starts looking like a world that took a catastrophic hit. Up to this point, you can still describe the far side as heavily cratered and older looking than the near side. That is true, but it is still not enough. Because once you get to the South Pole Aitken Basin, or SPA, you are not talking about normal lunar terrain anymore. You are talking about the largest impact feature on the Moon, and one of the most important impact structures anywhere in the inner solar system. The scale is the first thing that has to land hard. NASA describes SPA as more than 1,550 miles across, about 2,500 kilometers. That is enormous. It stretches across a huge fraction of the lunar far side. This is not the kind of crater people picture when they hear the word crater. It is not a bowl-shaped hole you can point to and move on from. It is a planetary scale excavation. It is so large that it changes the way you have to think about impacts in general. And that immediately raises the next question. If something is that wide, how deep did it go? NASA says the basin is about 6 miles deep on average, roughly 10 kilometers. And that depth changes the story completely. Because once an impact digs that deep, it is no longer just marking the surface. It is punching down into much lower layers of the Moon's crust, and maybe even getting close to the mantle. That means SPA is not just important because it is large. It is important because it may have exposed material from deep inside the Moon that normally would stay buried. That is why scientists care so much about it. In very simple terms, SPA may be one of the best natural drills in the solar system. No machine humans have built on the Moon has come close to doing what that impact did. It excavated a huge volume of material and may have brought deeper rock within reach of orbital instruments, landers, and future sample return missions. So now the far side becomes more than an impact archive. It becomes an access point. And then the timeline makes it even more serious. NASA places the formation of South Pole Aitken at roughly 4 billion years ago, back in the violent early era of the solar system, around the time often linked to the late heavy bombardment. That was the period when the rocky worlds were still taking major hits, when large collisions were not rare accidents, but part of how planets and moons were being reshaped. That matters because SPA is not just old. It is old enough to preserve evidence from one of the most violent phases in lunar and planetary history. So this is the moment where the Moon stops being local scenery and becomes hard evidence from the era when giant impacts were still changing worlds on a massive scale. And that leads to the next uncomfortable idea. What if this impact did more than carve a basin? NASA's own discussions of SPA allow for the possibility that the event was so huge it may even have affected the Moon as a whole body, possibly contributing to a reorientation of the Moon as it adjusted to that missing mass. Whether every part of that idea holds up or not, the main point is clear and strong. This was not a shallow surface event. This was not just something that broke the crust in one location. It was an event large enough to matter at the scale of the entire Moon. That is why SPA has to be framed as a wound, not just a minor feature. It is the result of an impact so extreme that it may have changed not only the far side, but the Moon's internal structure, mass distribution, and long-term history. It is a reminder that on planetary scales, collisions do not just leave marks, they can reorganize worlds. So why should you care this much about one basin? Because this is the point where the far side becomes much more than rough terrain with scientific interest. This is where it becomes target geology. South Pole Aitken is one of the best places on the Moon to test deep questions about how the Moon formed, how it separated into layers, how its crust and mantle evolved, and how giant impacts can tear into a rocky body and leave behind evidence that survives for billions of years. That is why NASA treats SPA as such a high-value objective. If rocks from deep crust or near mantle levels are exposed there, then samples from this basin could help answer some of the biggest lunar questions there are. Not just what hit the Moon, but how the Moon itself was built inside, how it cooled, how it differentiated, and how much of that early history is still physically reachable. That is a huge jump in stakes. Earlier, the far side was important because it preserved old impacts. Now, one of those impacts may have done something even more useful. It may have opened a window into the Moon's interior, and that changes how you look at the basin. It is not just a scar, it is a site where violence may have created access. A collision from the early solar system may have ripped open layers of the Moon that scientists still want to study directly. That is why SPA matters so much. It is not only evidence of destruction, it may also be one of the moon's best chances to reveal what lies underneath the surface history. So this section has to end with that pressure building. The far side is not just cratered, it contains the biggest impact basin on the moon. That basin is ancient, enormous, deep and scientifically loaded. It may preserve clues from the period when the inner solar system was being battered into shape. It may expose material from deep inside the moon. It may even record an event big enough to have affected the moon as a whole. And if that was not enough, NASA found something else under this basin that makes the entire story stranger. Because South Pole Aitken may not just be a giant hole left by an impact. It may still be hiding part of what hit it. NASA found something massive buried under that basin, and this is where the story gets much stranger. Up to this point, South Pole Aitken is already one of the biggest impact features in the solar system. Already old, already deep, already important. That would be enough on its own. But then NASA's Grail mission added another layer to the mystery. Under that basin, beneath the surface, there appears to be a giant dense mass that should not be sitting there in such a simple way. And this is the moment where it spikes, because now you are not just talking about a crater. You are talking about something hidden under the crater, something heavy enough to affect the basin itself. NASA describes it as a mysterious mass about 5 times larger than Hawaii's Big Island, pulling the basin floor downward by more than half a mile, around 0.8 kilometers. That is not a small anomaly. That is not a tiny local quirk in the data. That is a deep structural problem sitting under one of the moon's most important regions. So the obvious question is, how do you even find something like that if it is buried? NASA did not find it by taking a picture. Grail did not see a shiny object underground. It found it through gravity. That is what makes this part so good. Because it sounds almost invisible until you understand what the mission was actually doing. Grail used 2 spacecraft flying in formation around the moon, measuring tiny changes in the distance between them as they passed over places with different amounts of mass below the surface. That is the key idea. Gravity is not perfectly the same everywhere. If there is denser material under one region, the gravity there pulls a little harder. If there is less mass, the pull changes in the other direction. Those differences are tiny, but they are measurable. And when Grail mapped the moon with very high precision, the South Pole Aitken Basin did not behave like a simple giant hole in the crust. The gravity field said there was extra dense material below. That changes everything, because now the basin is not just a missing chunk of moon. It is a place where mass has been reorganized. And that leads to the next question. What is that buried mass actually supposed to be? NASA's leading interpretation is that it is probably metal-rich, and it may be connected to the asteroid that created the basin in the first place. In other words, part of the impactor may still be there, embedded deep in the moon, possibly in the mantle. That is a very serious possibility. It means the object that hit the moon hard enough to create South Pole Aitken may not have fully vaporized and may not have been completely scattered away. Some of it may still be trapped inside the moon after billions of years. That is a remarkable idea, because giant impacts are often imagined as events that destroy and disperse everything at the collision site. But this suggests that at least in some cases, an impact can leave behind not just a basin, but buried remnants of the impactor itself. So now South Pole Aitken becomes more than a scar. It becomes a scene with physical evidence still inside it. And this matters scientifically for a very big reason. Earth almost never preserves this kind of record cleanly. Earth is too active. Old giant impacts get erased, buried, recycled and altered. But if the moon really preserved impactor residue at this scale, then it gives scientists something extremely rare. Direct internal remains from an ancient mega-impact. That could help answer major questions about how giant collisions distribute metal, how deeply they penetrate, how basin floors settle over time, and how rocky bodies absorb truly catastrophic hits. That is not a side detail. That goes straight into planetary formation science. Because once you start thinking that way, the moon becomes a test case for processes that matter everywhere. How do giant impacts change the inside of a world, not just its surface? How much foreign material stays behind after a collision? How does a basin evolve if dense material is trapped below it? How do gravity, crust and mantle respond over billions of years after a hit that large? Those are the kinds of questions this buried mass forces scientists to ask. And that is why this is one of the strongest we were wrong beats. For a long time, the natural way to think about giant lunar basins was simple. A huge impact hits, excavates material, leaves behind a giant depression. And that is mostly the story. But NASA's gravity data says that picture is incomplete. Some basins are not just holes, they are places where matter was rearranged in a way that still affects the moon internally. The structure below the surface matters just as much as the shape above it. That is a major upgrade in how you see the far side. It is not only cratered on the outside, it is different on the inside too. The damage is not just visible, it is buried into the moon's internal structure. And that should make you pause, because this is where the moon stops looking passive. South Pole Aitken is not just a record of something that happened long ago and ended there. It is a place where that ancient collision may still be physically present, still detectable, still pulling on the crust above it. Billions of years later, the impact may still be shaping the basin floor through the mass left underneath. So the far side is no longer just an archive of old impacts. It is an archive with internal leftovers, with gravity anomalies, with deep structural consequences that survive from one of the most violent events in lunar history. That is why this section has to end by pushing the tension higher. NASA did not just map a giant basin. It found evidence that something dense and massive is still buried beneath it. Maybe metal-rich, maybe part of the asteroid itself, maybe one of the clearest surviving internal traces of a giant ancient collision anywhere close to Earth. And once gravity reveals that kind of hidden structure, the next question becomes unavoidable. If one mission could find a buried mass under the far side, then how much else did gravity mapping reveal about the moon's crust that surface images alone never could? Grail rewrote what NASA thought the far side's crust was like, because it showed the moon is not built like a clean shell. It is built like a body that got hit over and over and never fully healed. Before Grail, scientists already knew the far side was different. They could see the craters, the rougher terrain, the lack of huge morae compared with the near side. But there is a big difference between knowing a surface looks old and damaged, and knowing what that damage did to the crust underneath. That is where Grail changed the argument. NASA's Grail mission produced a lunar gravity map with resolution down to about 8 miles, around 13 kilometers. That may not sound dramatic at first, but this is much more than better data. This is detailed enough to separate major basin structures, complex craters, simple craters, and buried features in a way older gravity maps could not. It meant scientists were no longer limited to broad averages. They could start reading the moon's hidden structure in much finer detail. And that matters because once the resolution gets that good, the far side stops being just a photographed landscape. It becomes something you can analyze layer by layer. So the next question's, what did that higher resolution actually reveal? It revealed that the lunar crust is more fractured and more porous than people once thought. NASA reporting tied to Grail indicates an average crustal porosity of about 7 to 12%. In normal language, that means the crust is not a dense, uniform block of rock. It contains a lot of broken structure, void space, and impact damage. It is a shell that has been shattered, reworked, and weakened by repeated collisions over immense spans of time. That is a major shift in understanding. When people hear crust, they often picture something solid and continuous, like a clean outer layer. Grail says the moon's crust is much messier than that. It is battered material, mechanically altered by impacts again and again, and that changes how you interpret almost everything on the far side. Because now the far side's crater record is not just telling you what hit the surface, it is also telling you what those impacts did to the crust itself. They did not just leave marks on top, they changed the interior fabric of the rock. They cracked it, fractured it, opened voids and left behind a more complex mechanical structure than a simple map image could ever show. That is why Grail was such a turning point. It made hidden basin structure visible. Gravity data can show where crust is thinner, where denser material is sitting closer to the surface, and where old rings, faults, and buried structures still survive underneath later terrain. Topography can tell you what the surface looks like. Gravity can tell you what is helping hold that shape up. or what is hiding below it. That is a much deeper level of reading. So the far side stopped being a face and became a volume. That is the exact jump this section needs to make. Earlier in the script, NASA mapped the far side as a place. Now Grail maps what the far side hides. And once that happens, you should understand that this is no longer mainly about photography or terrain. It is about interior anatomy. It is about reading the moon as a three-dimensional body whose outer shell carries the mechanical consequences of billions of years of impacts. And that raises the tension again, because once you know the crust is fractured and porous, the far side becomes more than an ancient archive. It becomes a practical challenge too. A crust like that affects landing safety. It affects drilling. It affects how seismic waves travel. It affects how samples should be interpreted. If a rock comes from a crust that has been heavily impact processed, full of fractures and mixed structures, you cannot treat that sample the same way you would treat material from a cleaner geologic setting. The context gets more complicated. That is why Grail was not just a theory mission. It changed the exploration picture. It changed how NASA thinks about what is under a landing site, how basin structures are organised, how much hidden damage exists below visible terrain, and what subsurface material from the far side might actually represent. And this is important for another reason too. The more fractured and porous the crust is, the more every big impact starts to look like a restructuring event, not just a surface event. Impacts were not only carving basins, they were reshaping the mechanical properties of the moon's outer layers. That means the far side's heavily cratered appearance is not only a record of repeated collisions. It is also evidence that the crust itself was transformed by those collisions into a weaker, more broken, more complicated shell. So now the moon gets harder to simplify again. First, NASA showed the far side was different from the near side. Then it showed the far side had thicker crust. Then it showed the far side preserved more impacts. Then it found a huge buried mass under South Pole Aitken. And now Grail adds another layer. The crust itself is not a clean wall of rock. It is impact shattered, porous, and structurally uneven. That makes the far side more scientifically valuable, but also more demanding. If you want to land there, drill there, study seismic activity there, or collect deep samples there, you are not working on a simple world. You are working on a crust that has been mechanically changed by billions of years of bombardment. So this section ends with a very clear escalation. NASA did not just improve the map of the far side. Grail changed what the crust means. It showed that the moon's outer shell is more broken, more porous, and more internally complex than older models suggested. It revealed buried structure, hidden basin architecture, and a far side that is not only scarred on the surface, but altered through its crust. And once you know giant impacts reshape the crust that deeply, the next question becomes even more intense. Because if the far side's basins changed the crust from the outside in, then some of those impacts may have done even more than fracture rock. They may have exposed the moon's internal plumbing. NASA found that giant impacts on the far side exposed the moon's internal plumbing. And this is where impacts stop looking like damage and start looking like deep excavation. A lot of people still picture a crater as a hole, just a hole, maybe a big one, maybe a dramatic one, but still basically a dent in the surface. That idea is too small for what NASA found on the far side. The biggest impacts on the moon did not just smash the top layer and leave a mark. They excavated crust, moved huge amounts of material, pulled deeper layers upward, and reorganized the structure of the moon from below. This is where a basin stops being a feature and starts becoming a process frozen in rock. Oriental is the cleanest place to explain that. NASA's Grail analysis of the Orientale Basin mapped its gravitational field at about 3 to 5 kilometer resolution. That is extremely detailed for a basin this large. And the result was not subtle. NASA concluded that at least 3.4 million cubic kilometers of crustal material were removed and redistributed during the formation of that basin. That is not a normal impact in any everyday sense. That is crust being relocated on a scale closer to continents than craters. So the next thing you have to understand is simple. An impact like that does not only dig down, it also forces the moon to respond. That is where gravity data becomes so important again. NASA's Oriental visuals show that red gravity anomalies mark excess mass, and near the basin center, they point to especially thin crust and denser material closer to the surface, likely from much deeper levels. In plain language, the impact did not just blast material outward and leave an empty depression. The crust rebounded, deeper layers were pushed upward, the structure collapsed inward in places, rings formed, and the whole region was reorganized. That is the real picture of a giant basin. Excavation, rebound, uplift, collapse, redistribution, not a hole, a machine. And once you say that clearly, the far side looks very different. Those giant basins are not just records of how many times the moon got hit. They are records of what happens when a rocky world gets hit hard enough to expose its own interior. This is where Schrödinger comes in. NASA describes Schrödinger Basin, which sits inside the larger South Pole Aitken region on the far side, as the second youngest impact basin on the moon. It has about 3.3 kilometers of relief from rim to floor, and that alone already makes it a strong site for studying basin structure. But what really makes it powerful is how much it preserved. It still shows an inner ring. It has relays. It has volcanic deposits. NASA also describes a likely pyroclastic cone there. That means Schrödinger is not just an impact structure. It is a place where you can study both basin formation and what happened after the impact, including volcanic activity that followed. That makes it one of the best natural laboratories on the moon. So now you get a stronger idea of what these far-side basins really are. They are not static scars. They are giant geologic systems. They excavated crust. They uplifted deep material. They fractured the surrounding terrain. In some cases, they melted rock. In some cases, they opened paths that later volcanism could use. And because the far side preserved these structures so well, NASA can study some of the clearest surviving examples of how this entire process works. That is why this section matters so much. It upgrades the far side again. Earlier, the far side was important because it kept more of the impact record. Then it became more important because South Pole Aitken may expose deep material and even hide dense impactor residue below. Now it becomes more important again because the basins themselves show how planetary crust responds under extreme stress. The far side is not only a record of collisions, it is a record of planetary mechanics during collisions. And that gives you a much better way to explain it to the audience. A giant impact is not just a hit, it is an event that can remove crust, thin crust, lift deep dense material upward, rearrange the mass below the surface, and leave a structure that still holds that information billions of years later. The moon preserved that evidence far better than Earth ever could. So once you absorb this, the far side stops looking like random damage and starts looking like a controlled experiment in planetary violence. It shows how a rocky body reacts when the force is large enough to move mountains, displace millions of cubic kilometers of crust, and expose deeper layers without completely erasing the evidence afterward. That is why NASA keeps coming back to these basins. They are not just impressive landforms. They are physical records of how worlds absorb catastrophic energy. They tell you how crust breaks, how it rebounds, how mantle can be brought closer to the surface, and how the structure of a planetary body can be changed without being fully destroyed. And that pushes the story one step further, because once impacts are exposing deep layers and opening paths through the crust, a new question appears. If giant impacts could do all that, then maybe the far side was not volcanically quiet because it had no magma. Maybe volcanism was there too, just much harder to trigger, much rarer, and much more selective. NASA found the far side was not volcanically dead, it was just far more selective. And that difference matters a lot. A lot of people hear that the far side has fewer maria, and they jump to the simplest conclusion: no volcanism. But NASA's data does not support that. The far side had much less volcanic flooding than the near side. Yes, but that is not the same thing as saying nothing ever erupted there. The better way to say it is this: volcanism on the far side was harder, rarer, and much more limited by local conditions. That is an important correction, because the wrong version makes the far side sound empty. The real version makes it sound constrained. The magma was not completely absent. It just had a much harder time getting through. The far side has thicker crust. It preserved more impacts. Its basins exposed deep structure. So now the volcanic story becomes more precise. The near side was the easier route to the surface. The far side was the harder route, but not an impossible one. NASA's far side observations show basalt-filled features, lava infill in some basins, rilles, and even signs of explosive volcanism. That means the far side was not volcanically blank. It just never got reshaped on the same giant scale as the near side. The difference is not between activity and no activity. The difference is between broad flooding and selective breakthrough. Tsiolkovsky crater is one of the best examples because it makes this point in one image. NASA's far side visualizations specifically call it out, that dark, sharp-edged feature on the southern far side with the bright central peak. The dark material inside it is basaltic mare material. So magma clearly did reach the surface there. The far side was capable of producing volcanic fill. It just did not produce the same huge, familiar plains that dominate the hemisphere facing Earth. That is the key distinction you need to hear clearly. The far side did get volcanism. It just did not get continent-scale volcanic flooding in the same way. And once that clicks, the next example makes the point even stronger. Mare Moscoviense is another far side case NASA identifies clearly. It is one of the best proofs that Mare basalt exists on the far side, but in a much more limited and geologically specific setting. That is exactly what you would expect if the crust there was thicker and harder for magma to cross. Volcanism could happen, but not everywhere, and not easily. So these far side Maria are not contradictions to the main story. They are evidence for the more accurate version of it. They show that the crust was restrictive, not absolute. They show that under the right local conditions, likely where impacts thinned the crust or created structural weaknesses, magma could still make it to the surface. That is why the basin story and the volcanic story connect so well. Giant impacts were not only damaging the far side, in some places they may also have created the openings that later volcanism used. A basin could fracture the crust, thin it, and change the pressure conditions enough to make eruption possible where it otherwise might not have been. Then Schrödinger pushes the section one step further, because it shows the far side did not preserve only quiet lava activity. NASA describes Schrödinger Basin as having a likely pyroclastic volcanic cone, along with rilles and a smooth floor interpreted as lava infill. That matters because pyroclastic volcanism is more energetic and more complex than just molten rock quietly spreading out and cooling. So now the far side looks even less like a dead half of the moon. It has evidence of lava infill, basaltic deposits, structural pathways like rilles, and signs that some eruptions may have been explosive. That is a much more dynamic picture than the old oversimplified version. And this section really needs that correction, because if you only say the far side has fewer dark plains, the audience might hear less happened there. That is not the right message. A lot happened there. The difference is that the far side did not let volcanic activity spread as widely or as easily. Its crust and basin history controlled where eruptions could happen and how far they could go. So the far side is not the moon's dead half. It is the moon's restricted half. That is the stronger line. Because it matches the science better. NASA found a hemisphere where volcanism was more selective, more dependent on local geology and more limited by structure. The near side was more open to massive flood basalts. The far side allowed smaller, more isolated volcanic episodes in specific places where the crustal conditions were right. And once you frame it that way, the moon becomes even more interesting again. The same far side that preserved ancient impacts also preserved a more selective volcanic history. The same hemisphere with thicker crust and more battered highlands still found ways, in certain places, to let magma through. That means the far side is not just the place where volcanic flooding mostly failed. It is also the place where you can study what happened when it barely succeeded. That is why this section lifts the story instead of slowing it down. NASA did not find a dead hemisphere. It found a harder hemisphere, one where volcanism still happened, but under tighter rules. And that leads directly into the next escalation, because if giant impacts and selective volcanism opened deep pathways through the far side, then maybe some of the material now sitting on the surface did not come from the surface at all. Maybe the far side is showing us rock from deep inside the moon. NASA found clues that the far side may expose material from deep inside the moon. And this is where the story shifts from surface history to internal history. Up to now, the far side has already given NASA a lot. Thicker crust, more preserved impacts, giant basins, buried mass anomalies, and signs of selective volcanism. But this next step is even bigger, because now the question is not just what happened on the surface. The question is whether the far side may be showing us material that originally came from much deeper down, maybe even from the moon's mantle. NASA's 2021 interior work specifically identified likely locations where mantle material may be exposed at the surface, especially inside the South Pole Aitken Basin. The idea is that the basin-forming impact was so violent that it may have excavated deep material and thrown it into places where it can now be studied. That is the first thing to make very clear. South Pole Aitken may not just be a giant scar. It may have done the digging for us. NASA's work used the distribution of thorium across the basin to help map where deep material may have been excavated and left accessible. That does not mean every high thorium patch automatically equals mantle rock, but it does mean scientists now have specific targets instead of a vague hope. This is a major shift because it turns the far side from a general place of interest into a set of concrete candidate locations where the moon's deeper layers may already be exposed. And this is where the section gets much stronger, because NASA did not leave it at somewhere in the basin. It pointed to two especially important spots. NASA notes that two craters in the northwestern part of South Pole Aitken show especially high thorium abundance, suggesting that abundant deep material may be exposed there. That is exactly the kind of detail that changes the feeling of the story. Now, you are not talking about an abstract possibility. You are talking about real places on the far side where NASA thinks the moon's interior may already be sitting close enough to study directly. So why does that matter so much? Because if a future mission can collect real mantle material, then scientists can test some of the biggest ideas about how the moon formed and evolved. They can test models of the lunar magma ocean, the idea that the early moon was once largely molten. They can test how the moon differentiated into layers, crust on top, mantle below, with different chemistry and minerals separating as the interior cooled. They can test how heat moved through the moon, and how the moon's thermal evolution shaped everything we see today. In plain language, a mantle sample would connect the far side directly to the moon's birth. That is why this section matters so much for pacing. Up to this point, giant impacts have mostly looked like destructive events. Now that they become delivery systems, a huge collision may have ripped open the crust and thrown deeper material into places where later missions could actually reach it. That means the violence of the early moon may have accidentally made some of its oldest internal history accessible. And the case does not rely on only one kind of evidence. Grail gravity, results, and topographic analyses keep reinforcing the same broad picture. NASA's gravity work on major basins shows places where the crust is especially thin and where denser material sits closer to the surface. That does not prove that every promising site contains pure mantle rock ready for collection. Scientists still have to be careful there, but it strongly supports the larger idea that the far side contains some of the moon's best windows into deeper layers. And once that clicks, the far side changes again. It is no longer just the moon's oldest looking hemisphere. It is no longer just the impact archive. It is no longer just the place with the biggest basin and the buried mass anomaly. It becomes something more valuable than all of that put together, a place where the moon's internal history may have been ripped open and left within reach. That is the payoff line for this section. NASA did not just find that the far side is ancient. NASA found that it may be one of the few places where the moon's deep interior has been exposed by violence and left accessible to science. That is a much bigger statement, because now the far side is not only preserving events, it may be exposing origin. And once you reach that point, the next question becomes even more interesting, because if deep lunar material really got exposed on the far side, then the chemistry there should not always fit the simple picture people expect. And NASA found exactly that. Chemical clues on the far side that do not fully follow the neat story. NASA found far side chemistry that does not fit the simple story, and that matters because the moon keeps refusing to stay neatly divided into one hot side and one cold side. By this point, you could be tempted to think the pattern is clean. Near side, more volcanism, more dark plains, more heat-producing chemistry. Far side, thicker crust, fewer Maria, more craters, less volcanic flooding. That basic picture is still useful, but NASA found something that complicates it. And this is exactly where the science gets better, because real worlds are not tidy, and the far side has chemical traces that do not fully obey the easy version of the story. The fastest way to explain this is with one word: creep. That is shorthand for material enriched in potassium, rare earth elements, and phosphorus. These are chemically evolved leftovers from the moon's early history, and they matter because they are tied to thorium enrichment and to heat production inside the lunar crust. In simple language, creep-rich material helps explain why some parts of the moon stayed volcanically active longer, and why the near side ended up with more prolonged flooding by basalt. NASA's lunar science work has long tied these enriched materials mainly to the near side, so the rules sound straightforward. Most of the creep-rich terrain is on the near side. That fits the larger pattern of near-side volcanism. That fits the idea of asymmetry. That fits the idea that one hemisphere had more heat-producing chemistry, helping magma stay active and reach the surface. And then NASA gives you the exception. In the Van de Graaff region, on the far side, NASA notes that the crater and surrounding terrain are slightly enriched in thorium. That is the key detail, because thorium is one of the clearest markers tied to creep-rich material. And NASA explicitly points out why this is intriguing. Most of the moon's creep-rich materials are found on the near side, so seeing enhanced thorium there on the far side does not fit the simple expectation. And this was not just one modern mission producing one strange result one time. NASA's older Apollo gamma ray work already reported an enhanced region of natural radioactivity around Van de Graaff on the far side. So this is not some one-off artifact from a single map or a modern overinterpretation. It has shown up across different eras of lunar investigation, from Apollo-era orbital gamma ray analysis to later NASA discussions of thorium enrichment in the region. That makes the anomaly much more serious. So now the question becomes, what does that actually mean for the bigger story of the moon? It means the moon's internal differentiation and chemical history were probably messier than the cleanest version of the asymmetry model suggests. If the far side really hosts isolated patches of chemistry usually associated with the near side, then the moon was not simply divided into two perfectly separated chemical worlds. Some materials may have been redistributed by impacts. Some enriched zones may have had more complex origins. Some thermal and magmatic processes may have crossed the neat boundary that people like to imagine between the two hemispheres. That does not mean the whole near side versus far side story collapses. It does not. The asymmetry is still real, and NASA's data still supports it strongly. But this far side thorium anomaly is a serious complication, and complications are where the science becomes more convincing, because if every detail fit too perfectly, the story would look suspiciously clean. Instead, NASA found a moon that preserves the main pattern, but also preserves exceptions that force scientists to ask harder questions. Did impacts move chemically, evolved material, farther than expected? Did basin-forming collisions excavate and redistribute enriched rock into unusual places? Did some far-side regions preserve traces of processes that were more widespread early on and later became concentrated on the near side? Those are the kinds of questions this anomaly opens up, and that is why this section helps the pacing so much. It stops the documentary from becoming too neat. It reminds you that NASA did not find a perfectly organised far side where every fact points in one simple direction. It found a hemisphere that preserves the moon's asymmetry, yes, but also preserves leftovers from processes that crossed that asymmetry, complicated it, or partly broke the clean pattern. That is exactly the kind of thing you want in a high-intensity science story, because it means the moon is not just strange in one way. It is strange in layers. So the takeaway here is very direct. NASA found that the far side does not only preserve a different crust, different volcanism, and a harsher impact record. It also preserves chemical clues that do not fully match the easy near side versus far side split. Van de Graaff is one of those clues, and it matters because it says the moon's internal story was not perfectly sorted. Some of the chemistry leaked across the boundary, or got thrown across it, or survived there in ways that still need explaining. And once the far side starts showing chemical exceptions, as well as structural ones, the tension rises again. Because now you are forced to ask a different question. If parts of the far side can preserve strange chemistry, then what about the places that really are dark? Not the whole far side, but the crater floors near the poles where sunlight never reaches. Because that is where NASA found something else that changes the moon from an archive into a resource. NASA found that the far side's south polar darkness can preserve ancient ice, and this is where the word dark finally becomes scientifically real. The far side is not permanently dark. That part is still wrong. But some places near the lunar poles really do stay in darkness for extremely long periods. NASA explains that the moon's axis is tilted by only about 1.5 to 1.6 degrees, so sunlight never reaches the floors of some deep craters near the poles. These are the permanently shadowed regions, or PSRs. That is the part of the moon where the old dark side language stops being myth and starts touching something real. And once you understand that, the next question gets serious very fast. Because what happens to a place that sunlight cannot reach for millions or even billions of years? It gets brutally cold. NASA's LRO material says these permanently shadowed regions are among the coldest places in the solar system, and temperatures in deep polar shadows can fall below minus 410 degrees Fahrenheit, about minus 246 degrees Celsius. That is not just cold by Earth standards. That is cold enough for water ice to remain stable over very long timescales if it gets trapped there. That is why these regions matter so much. They are not just dark holes in the terrain. They are cold traps. If water molecules delivered by comets, asteroids, the solar wind, or ancient volcanic processes migrated across the moon and found their way into those shadowed crater floors, the extreme cold could keep them there for immense lengths of time. In other words, the darkness is not just a visual feature. It is a storage system, and NASA did not build that case by guessing. This part is important to say very plainly. NASA did not just look at a cold crater and assume there must be ice inside. LRO used multiple instruments that approach the problem in different ways. NASA says the Lunar Exploration Neutron Detector, or LEND, identified hydrogen-rich areas by measuring neutrons, and hydrogen is a major clue for water or hydroxyl-bearing material. At the same time, the Lyman Alpha Mapping Project, or LAMP, used ultraviolet light, including faint starlight and interplanetary glow, to probe permanently shadowed regions and detect surface properties consistent with water frost or ice. Those are independent physical measurements pointing in the same direction. That makes the story much stronger. This is not maybe wet dirt because someone wanted the moon to be useful. This is a layered scientific case built from temperature, lighting geometry, neutron measurements, and ultraviolet observations. The far-side adjacent south polar darkness is valuable because NASA can tie the argument to actual instrument data, not just speculation. And the far side matters here for another reason too. The lunar south polar terrain is not separate from the larger far side story. NASA notes that features like the Malapert Massif near the South Pole are thought to be remnants of the South Pole Aitken Basin rim. So when NASA studies darkness, ice stability, and access near the South Pole, it is also working inside terrain connected to the moon's biggest and oldest giant impact structure. That means geology, temperature trapping, and exploration value are all stacked together in the same region. That is why this section upgrades the moon from archive to outpost. Earlier, the far side mattered because it preserved ancient impacts, deeper structure, and clues to the moon's internal history. Now it matters for another reason. Some of the moon's most inaccessible darkness may also hold one of its most useful resources. Ancient ice could mean water for life support, oxygen extraction, and even propellant production if future missions can reach and process it. At the same time, those cold traps may preserve chemical history that has been stored for millions or billions of years in near deep freeze conditions. So the far side and south polar darkness are no longer just scientifically interesting in an abstract way. They become operationally important too. NASA found that some of the harshest, coldest, hardest to reach places on the moon may also be some of the most valuable. That is a major change in the story, because the far side is not only a record of the past anymore, it starts to look like part of the infrastructure for the future. And once you see that, the tension should rise again, Because if the far side and polar regions are not only ancient and resource-rich, but also naturally shielded from Earth in some ways, then their value does not stop at geology or ice. It extends outward into astronomy, because NASA found that the far side may be one of the quietest radio environments in the inner solar system. And this is where the story stops being only about the moon and starts reaching into the early universe. Up to now, the far side has looked like an archive, a place that kept ancient impacts, deeper structure, and maybe even ice. But this section changes the scale completely. NASA is not only interested in the far side because of what is on it. NASA is interested in it because of what it blocks. The moon itself can shield the far side from Earth's radio noise, and that makes it one of the best places anywhere near Earth to do very low-frequency radio astronomy. NASA's far-side radio work and mission concepts keep coming back to the same point. Some long radio wavelengths cannot be studied properly from Earth because our ionosphere blocks them, and our technology fills nearby space with radio interference. The far side removes both of those problems at once. On Earth, even if you build a perfect telescope, Earth itself gets in the way. The ionosphere blocks radio waves at about 10 meters, around 33 feet, and longer. And human civilization adds constant radio chatter on top of that. NASA's Lunar Crater Radio Telescope concept states this directly, and NASA's LUSE night announcement says, those dark ages signals are impossible to measure from Earth's surface because of the opaque ionosphere and Earth's radio pollution. So the far side is not just quiet, it is shielded. The moon becomes a physical wall between a delicate instrument and the noise coming from Earth. And that is why NASA's language about the far side gets so strong. In the LUSE night announcement, NASA says the far side offers a unique environment for observing sensitive radio signals that cannot be obtained anywhere else in the near-Earth space environment. In the LCRT concept, NASA says the far side could be prime real estate for unprecedented studies of the early universe. That is a big jump in stakes, because now the far side is not only a place to study lunar rocks, it is a platform for cosmology. So what exactly would scientists try to hear there? NASA keeps pointing to the same target, the cosmic dark ages. That was the period after the universe became transparent but before the first stars and galaxies lit up. NASA explains that this era may be probed through long wavelength radio signals, especially the highly redshifted hydrogen signal, and that those observations could reveal how the first large structures formed and how the universe moved from darkness into the era of stars. In plain language, the far side could become a listening post for one of the earliest chapters of cosmic history that we still do not understand well. That changes the meaning of the moon immediately. The same hemisphere NASA mapped as an ancient impact archive may also be one of the best places to study the dawn of structure in the universe. The far side is doing two jobs at once. It preserves the history of a battered rocky world, and it may also let us detect signals from a time before stars existed. That is a very different kind of scientific value. But NASA also makes clear that this opportunity comes with a harsh constraint, and that is where the tension rises again. These observations are best done during the lunar night, when the far side is not only shielded from Earth, but also from the sun's radio emission. NASA says LUSE night is designed to operate during the 14-day lunar night, and NASA notes that the far side is shielded from harmful radio emissions from Earth and from the sun during that time. So the best science window is also the hardest survival window. That makes the engineering challenge part of the drama, not a side note. During the lunar night, there is no sunlight for power or heat. Temperatures plunge, and the far side has no direct line of sight to Earth. NASA says LUSE night has to survive the harsh, cold, dark conditions long enough to collect and return data, and that technology for surviving the lunar night is critical for long-duration science on the moon. So the far side's radio promise is tied directly to some of the most punishing operating conditions in lunar exploration. That is the payoff for this section. The farther you go into the far side story, the less it looks like the moon's hidden back, and the more it looks like one of the most strategically valuable pieces of terrain near Earth. It can preserve ancient impact history, maybe expose deep lunar material, maybe hold ice in permanent shadow, and at the same time act as a shielded observatory for radio signals that Earth cannot study properly. NASA did not just find a rougher hemisphere, It found a hemisphere that may matter for geology, resources, and cosmology all at once. And once the far side starts looking that valuable, the next question gets sharper. Because if this hemisphere is scientifically active in so many ways, then the old idea of the moon as dead and finished becomes harder to defend. NASA's own data says the moon is not as dead as it looks, and the far side is still missing one of the most important measurements of all, its own seismic voice. NASA found the moon is not as dead as it looks, and the far side is still missing one of the most important measurements of all. A lot of people talk about the moon like it is finished, cold, silent, geologically dead, just sitting there unchanged. NASA's own data says that picture is too simple. The moon is quieter than Earth, yes, but quiet is not the same as inactive. NASA-funded work using LRO data shows the moon is still shrinking as its interior slowly cools, and that contraction is creating thrust faults and moonquakes, including hazards near the South Polar region. In other words, the moon is still adjusting to its own ancient heat loss right now. That is the first uncomfortable point this section needs to land. The moon is not erupting like Earth, and it does not have plate tectonics like Earth, but that does not mean nothing is happening. As the interior cools, the whole body contracts. NASA describes this process clearly. The crust breaks and one block is pushed up over another, forming thrust faults. Those faults are not just old fossils from some distant era. NASA's work says some are still active and likely producing moonquakes today, and that gets stronger when you see how widespread the evidence is. NASA says LROC has revealed thousands of young lobate thrust fault scarps across the moon. One NASA release says more than 3,200 of these fault scarps had been identified, globally distributed across the lunar surface. Another NASA LRO summary says scientists found hundreds of previously undetected scarps in LRO images, and that many of them formed much less than 1 billion years ago, with some possibly as young as about 50 million years. That is very young in lunar terms. It means the moon is not just preserving an ancient frozen past. It is still changing, slowly, as it contracts. That is the line that changes the moon from a museum into a body still responding to its own history. The scarps are the surface expression of contraction. They are the visible record of a world still settling, still losing heat, still breaking in places under that stress. And NASA's South Pole work raises the stakes even more. Because it says shallow moonquakes tied to these faults can be strong enough to matter for future exploration. One NASA study linked a young thrust fault scarp near a candidate Artemis III region to shaking that could match the strongest shallow moonquake recorded by Apollo. The far side is still a seismic blank spot. That is a major gap in the story. Apollo gave us seismic data, but Apollo operated on the near side. So even though NASA has mapped the far side in detail from orbit, and even though gravity, topography, and imaging have transformed our understanding of it, we still do not have direct far side seismic measurements from the ground. That is exactly why NASA's upcoming far side seismic suite exists. JPL says FSS will place 2 sensitive seismometers on the far side to measure far side moonquakes and meteor impacts for the first time ever. That single fact should hit hard. We know the far side is asymmetric. We know it has thicker crust. We know it preserves more impacts. We know it contains major basins, buried dense mass, and complex crustal structure. But one of the most important direct data sets is still missing, the far side's own seismic voice. And that gap matters for a very specific reason. NASA says far side seismic suite data will help explain why Apollo detected so few quakes, apparently associated with the far side, and will help determine whether far side seismicity truly differs from near side seismic activity. It will also improve our picture of the moon's interior structure and record background vibrations caused by micrometeorite impacts. So this is not just about filling in a blank on a map. It is about testing whether the far side is dynamically different in the same way it is structurally different. That is why this section should feel like unfinished business. NASA has already found enough on the far side to prove the moon is not simple, not symmetrical, and not fully inactive. The moon is still shrinking. It still forms thrust faults. It still experiences moonquakes. The far side is already known to be geologically and structurally distinct. But until seismometers actually listen from that side, one of the biggest questions is still open. Does the far side really quake differently from the near side? NASA has enough evidence to overturn the old idea of the moon as dead and fully understood, but not enough yet to close the case. The far side is still hiding one of the most important datasets of all, direct ground truth from inside the crust. So the takeaway here is very clear. NASA found the moon is still contracting and still capable of moonquakes. NASA found thousands of young thrust faults that show the surface is not finished adjusting. And NASA also found that, for all the far side mapping already done, the far side remains the missing seismic piece in the moon story. And once you say that out loud, the next section gets even sharper. Because if the far side is this scientifically valuable, and this much is still missing, then reaching it was never going to be easy. NASA found that getting to the far side means fighting the moon on every system: communications, temperature, terrain, power, and survival. NASA found that reaching the far side means fighting the moon on every system, and that is exactly why the science there matters so much. The first problem is the most basic one, and it never goes away. From the far side, you do not have a direct line to Earth. The moon itself blocks it. NASA's lunar communications work says surface assets on the far side, and in some polar regions cannot communicate effectively with Earth without a relay. And NASA's relay architecture planning treats those relay systems as required infrastructure, not optional extras. That means if you want to land there, drive there, listen there, or survive there, you have to solve communications first. The far side is scientifically rich for the same reason it is operationally difficult. It hides behind the moon. And that one fact changes the whole way you think about lunar exploration. On the near side, at least in principle, you can talk directly home. On the far side, you cannot, or not say, that means relay orbiters, relay satellites, or companion spacecraft are not support equipment in the background. They are part of the mission's core life support for data, navigation, and command. Without that chain, the far side is cut off by geometry alone. Then the thermal problem makes it worse. NASA's lunar temperature data shows sunlit terrain can climb to about 250 degrees Fahrenheit, around 121 degrees Celsius, while deep permanently shadowed regions can fall below minus 410 degrees Fahrenheit, about minus 246 degrees Celsius. On top of that, the lunar day-night cycle is brutal, roughly 2 Earth weeks of sunlight followed by roughly 2 Earth weeks of darkness. NASA engineering work on lunar operations notes that surface systems must both dump heat during the day and survive temperatures below 100 Kelvin during the long lunar night. That is not a normal engineering environment. It stretches thermal control, battery survival, insulation, and heater design to the limit. That is the key point for you. The far side does not only challenge hardware because it is remote. It challenges hardware because the moon gives you almost no environmental mercy. If your system is in sunlight, it risks overheating. If it is in darkness, it risks freezing. And if your mission needs the far side during the long lunar night, which some radio astronomy concepts do, then the most scientifically valuable operating window is also one of the hardest survival windows. The moon also does not help you survive in any ordinary way. NASA's Moon Facts page says the moon has only a very thin and tenuous exosphere, not a breathable atmosphere. That means no pressure, no weather shield, no useful protection from radiation, and no meaningful protection from incoming micrometeoroids. The moon's surface gravity is only about 1/6 of Earth's, which sounds easier until you remember that low gravity changes landing behavior, dust motion, traction, mobility, and structural loading in ways engineers still have to manage carefully. NASA's lunar dust work also treats dust as a serious operational problem, not a small inconvenience. So by this point, the pattern is clear. Communications are harder, thermal survival is harder, surface operations are harder. Human survival would be harder, instrument survival would be harder. The far side is not difficult because NASA has not tried enough. It is difficult because every major system has to work in an environment with no atmosphere. Long blackouts, extreme temperatures, low gravity, and abrasive dust all at once. And yet NASA keeps choosing it. That is one of the strongest signals in the whole documentary. NASA is not developing relay architectures, far-side seismic missions, radio observatory concepts, and communication standards for the far side because it is easy terrain. It is doing it because the science return is too large to ignore. NASA studies for far-side radio astronomy describe the far side as uniquely shielded for low-frequency observations, and NASA's geophysical network planning explicitly includes relay support for far-side landers because the science case is strong enough to justify the added infrastructure. The difficulty is part of the evidence for the value. That is the line this section has to land on. NASA did not just find weird features on the far side and get curious. It found a region so scientifically loaded that agencies are willing to solve communication blackouts, extreme temperature swings, long power survival, dust risk, and remote operations just to work there. Every earlier discovery gets heavier once you realize that. The thick crust matters more. The impact archive matters more. South Pole Aitken matters more. The buried dense mass matters more. The polar ice matters more. The radio silence matters more. All of it becomes more convincing when you see what NASA is willing to build to get there. So this section sets up the ending very clearly. The far side is not valuable, despite the engineering pain. It is valuable enough to justify the engineering pain. NASA found a place where communications are blocked, nights are long, shadows are cryogenic, dust is a problem, and basic survival is hard, and still kept coming back. That tells you the far side is not a curiosity. It is one of the most strategically important regions on the moon, and once you see that, the finale becomes obvious. NASA did not find that the far side was simply the moon's back. It found that the far side may be the moon's truth serum, the place where the easy story breaks, and the real moon finally shows itself. The real conclusion is that NASA did not find the moon's back. It found the place where the simple story about the moon stops working. At the start, the first thing to kill was the phrase dark side. That phrase survives because it sounds dramatic, but also because people were sensing something real underneath it. They knew the hidden half of the moon had to matter. They just described it badly. NASA replaced that bad description with measurements, surface maps, topography, chemistry, gravity, temperature data, lighting data, and soon more far-side seismic data. All of it points to the same result. The far side is not just unseen, it is fundamentally different. And once you say that clearly, the whole documentary snaps into place. Because what NASA actually found was not one shocking object, or one perfect answer, or one headline discovery you can reduce to a meme. NASA found a whole stack of discoveries sitting on top of each other. A hemisphere with thicker crust, a hemisphere with fewer mare basalts, a hemisphere that preserved more impact scars because less resurfacing wiped them away, a hemisphere that contains the biggest impact basin on the moon, a hemisphere where gravity data points to a giant, dense buried mass under that basin, a hemisphere where giant impacts may have exposed material from deep inside the moon, a hemisphere with chemistry that does not always follow the easy rule, a hemisphere with south polar cold traps that can preserve ancient ice, and a hemisphere that may be one of the best radio-shielded locations in the inner solar system for studying the early universe. That is not one discovery. That is a hierarchy of discoveries, and that is exactly why the far side matters so much, because the old mental model of the moon is too simple. One side we know, one side we do not see. Same basic world all the way through. That is the version people carry around in their heads. NASA's findings break that model apart. The far side is not just hidden territory that happened to be out of sight. It is the half of the moon where multiple deep problems come together at once. Asymmetry, impact history, crustal structure, deep excavation, volatile trapping, engineering difficulty, and even future astronomy. That is why the far side forces every oversimplified lunar story to collapse. It is where the moon stops looking uniform. It is where the moon stops looking finished. It is where the moon stops looking like a passive companion world. The far side keeps showing that the moon is structurally uneven, geologically selective, thermally important, mechanically damaged, chemically more complicated than the cleanest models suggest, and still central to future exploration. So by the end, the answer to the question, what did NASA find on the dark side of the moon, is not aliens, not secret bases, not a hidden city, not any of the nonsense that survives because it is easy to repeat. NASA found something much more important than that. It found a hemisphere that preserves the moon's deepest asymmetries and may hold one of the clearest surviving records of how rocky worlds are built, broken, flooded, frozen, and studied. That is the strongest final line because it is bigger than a twist. It is a correction to how people think about the moon itself. The far side is where giant impacts are easier to read. It is where the crust tells a different story. It is where volcanic failure and selective breakthrough both show up. It is where some of the best windows into the deep moon may exist. It is where ancient ice may survive in permanent darkness. It is where the moon can block Earth's noise and turn itself into a platform for listening to the early cosmos. And it is where some of the most important ground truth is still missing, which means the far side is not just a solved mystery. It is still an active frontier. That is the real escalation at the end of all this. The farther NASA pushed into the far side, the less the moon looked like a dead companion to Earth, and the more it looked like a master archive. An archive of planetary formation, an archive of giant impacts, an archive of crustal evolution, an archive of trapped volatiles, maybe even a platform for detecting signals from the earliest large-scale structure in the universe. So the moon did not become stranger because scientists exaggerated it. It became stranger because science finally got close enough to measure what was really there. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.